Hello, very good morning to my dear students. Today we will discuss about the Ferranti effect for a transmission and distribution system. We will discuss about what is Ferranti effect. Normally in transmission line, the receiving end voltage is less than the sending end voltage due to the voltage drop and voltage are losses in transmission line. But in Ferranti effect, the receiving end voltage is more than the sending end voltage. So this effect is known as Ferranti effect. We will discuss about the definition of Ferranti effect. The effect in which the voltage at the receiving end of the transmission line is more than the sending voltage is known as the Ferranti effect. Such type of effect mainly occurs because of the light load or the open circuit at the receiving end. Ferranti effect is due to the charging current of the line when the alternating voltage is applied. The current that flows into the capacitor is called the charging current. A charging current is also known as the capacitive current. The charging current increases in the line when the receiving end voltage of the line is larger than the sending end voltage. This effect is known Ferranti effect. Next we will discuss about the why Ferranti effect is occurs. Capacitance and the inductance are the main parameters of the line having a length is more than 240 kilometers or above. On such a transmission line, the capacitance is not concentrated at some definite points. It is distributed uniformly along the whole length of the line. When the voltage is applied at the sending end, the current drawn by the capacitance of the line is more than the current is associated with the load. Thus, at the no load or light load, the voltage at the receiving end is quite large as compared to the constant voltage at the sending end. Next, we will discuss detailed explanation of the Ferranti effect by consideration a nominal pi method. As shown in diagram, nominal pi method for a transmission line, there are two capacitors are used in both sides, sending end side and receiving end side. Also the capital R is the resistance and X is the inductance of the line as shown in diagram. Let us consider the long transmission line which OE represent the receiving end voltage, OH represent the current through the capacitor of the receiving end side. The phasor FE is represent the voltage drop occurs in the resistance capital R. The voltage drop occurs across the inductance capital X. The phasor OG is represent the sending end voltage and VR is equal to receiving end voltage, over here is Vs is sending end voltage, and connected power AC power supply to the circuit diagram. Next we'll discuss about it is seen that the phasor diagram are as shown in diagram. Let's the OE is greater than OG. In other words, the voltage at the receiving end is greater than the voltage at the sending end when the line is at no load condition. As shown in phasor diagram, over here is IC1 is the capacitor current, and OG is equal to sending end voltage, OF is equal to receiving end voltage. Over here is XL, X IC1, and over here is I into RC1. Next we'll discuss in details. Vs minus Vr is equal to Yz divided by 2 into Vr. Over here is Z is equal to small r plus j omega L into S. Y is equal to j omega C into S. At no load condition, IR is equal to 0. So Vs is equal to 1 plus Zy divided by 2 into Vr. And let's Vs is equal to Vs minus Vr is equal to 1 plus Zy divided by 2 and into Vr minus Vr. So Vs minus Vr is equal to Vr in bracket 1 plus y into z divided by 2 minus 1. Next, if the resistance of the line is neglected, so Z is equal to j omega L into S, and Vs minus Vr is equal to 1 upon 2 j omega Ls into j omega Cs into Vr. So final equation is Vs minus Vr is equal to minus 1 by 2 omega square S square into IC into Vr. For overhead transmission line, 1 upon under root IC is equal to velocity of the propagation of the electromagnetic waves on the transmission line. Next we will discuss about under root IC is equal to 1 upon 3 into 10 raised to 0, and IC is equal to 1 upon 3 into 10 raised to 8 raised to 2. So Vs minus Vr is equal to 1 by minus 1 by 2 omega square S square 1 upon 3 into 10 raised to 8 raised to 2 into Vr. So the above equation shown that the Vs minus Vr is the negative, that is Vr is greater than Vs. This equation is also shows that the Ferranti effect also depends on the frequency and the electrical length of the line. In a general form, any line I into R is equal to 0 and Vr is equal to VRL, Vs is equal to A into VRL L. So finally VRNL is equal to Vs means sending end voltage divided by A. For a long transmission line, A is less than unity and decreases with the increase in the length of the line. Hence, the voltage at the no load is greater than the voltage at the load. So VRNL is greater than Vs. As the line length increases, the rise in the voltage at the receiving end at no load becomes more predominant. Means in Ferranti effect is also depends on the length of the conductor, and it is depends on the voltage level. Last we will discuss about how to reduce the Ferranti effect. By using electrical devices are designed to work at some particular voltage. If the voltage are high, at the user's ends, their equipments gets damaged and their windings burns because of the high voltage. In Ferranti effect on long transmission line at low load or no load increases the receiving end voltage. This voltage can be controlled by placing the shunt reactor at the receiving end of the lines. Also, shunt reactor is an inductive current element connected between the line and the neutral to the compensate the capacitive current from a transmission line. When this effect is occurs, long transmission line, shunt reactors, compensators and the capacitive VAR of the lines are used. Thank you.